just in like the culture of like just coming and getting help, which seems like a really simple thing, but like, like I always used to find that sort of like every lunch and every day after school, I'd have like 3 or 4 kids, 5 kids sometimes getting math help or getting chemistry help or getting physics help. And if you're getting it somewhere else, great, like that's fine. But like, that was always encouraging, because like people are only coming to get help if they're like trying the work and discovering that they can't do it. You know what I mean? So that's when people are coming for help, it's an indication that people are trying to do the work. And then the other thing is, it's then a chance for people to get help and get better at it. Does that make sense? So like, that's a good habit of mind. You're not a rock, you're not an island. Everyone needs help, everyone needs support sometimes. So just when in doubt, don't be shy. Come get help with what you're doing. Okay, let's get talking. A chemical reaction. What's that? What's a chemical reaction? Sorry? Yeah, good. And what's it mean? Because we used react in our sort of definition, which is fine. But like we say, we form a new compound. Fundamentally, what's happening? Like if I don't know, get some water and boil it, is that a chemical reaction? No. In fact, if you remember from grade 9 science, we qualify that as a physical change, not a chemical change. Why? Yeah. In fact, it never leaves its original state. Like, weird as it is to think of a gas and a liquid being the same thing, but liquid water and gaseous water and ice are all the same thing. They're just kind of packed differently. In the case of ice, you've got these water molecules held tightly together so they can't move around away from each other. We call that a solid. If you warm it up a bit, they're able to kind of move freely away from each other, though they're still connected. We call that a liquid. And then you warm it up enough, they move completely independently of each other. We call that a gas. But what is every particle at every point? It's still H2O. It's still water. So we don't call that a chemical reaction. We call that physical change. For it to be a chemical reaction, you'd have to start off with H2O and end up with different actual particles. Does that make sense? And that's going to be our working definition of a chemical reaction then. We're going to say that in a chemical reaction, bonds between atoms are made or broken, or both, so what are signs that a chemical reaction has occurred? They're not guarantees, they're not evidence of, but they're indications of. What are some signs that a chemical reaction might have happened? Yeah, so a change in color. Sure. I'm not going to write that, not because it's bad, but just because it sort of assumes some prior knowledge. We're talking pH and things like that, but it's a good one, yeah. Yeah, good. The formation of a solid. Now, again, that in and of itself, that could just be freezing, right? So this isn't a guarantee, but the formation of a solid from liquids. Does anyone know what that's called? This is the most annoying term because it sounds like a completely different thing. Sorry? I mean, that's what it is. It's called precipitation, which is so annoying because that's also what we call it when water falls out of the sky. So that's a stupid double use of a word. But yeah, we say it's a precipitate when a solid forms from mixing two liquids. What else? Common things. So we could have a change in optical clarity. Sure, but that again, it's important to remember with all these, that isn't a guarantee because that could also just happen when you dissolve something. That's not a chemical change. Yeah. Sure. Yep. Gas is forming. And usually with that, we would look for smoke or bubbles or things like that. Bubbles are a big one. A lot of reactions now, again, not a guarantee, because that could also just be boiling water, right?
If you can like drink it, could you tell by the taste?
Yeah, taste would change. I'm not going to write that because I don't want anything in my notes that implies that I want you to eat chemicals. But you're right, you would get change in taste. I'm missing some big ones. When you think of chemical reactions, what's the kind of thing people, especially like a grade 9 boy? If I say, grade 9 boys, what do you think chemistry is? Explosions. Fire. Except they're in grade 9, so like, fire! Explosions! Right, but other than that, I had it right. Yeah, so which really, when you have a fire or an explosion, what is that? What are the things you're observing? Well, that's the reaction, but what are the signs? What my friend? Ruby's got tests in there for you if you want to try up, and we'll have to find your spot. Yeah. Heat, right? Heat released or absorbed. Obviously, in that reaction, it's releasing heat, but some reactions absorb heat. What else? A fire isn't just releasing heat, it's also releasing, I guess, light, right? Sound. Lights, camera, action. Does that make sense? Now again, does any one of these guarantee that a chemical reaction is happening, right? You turn a gas heater on, that's producing heat by way of a chemical reaction, right? If you turn your furnace on at home and you have a gas furnace. Probably most of you have a gas furnace. On the other hand, if you have an electric heater, that's not a chemical reaction. That's a whole different thing. That's just electricity. Does that make sense? So no one of these things guarantees a chemical reaction is happening, but they're all evidence that one might be. Does that make sense?
Yeah.
Cool. All right. So now, having said that, the whole point is the reason we see these things is because at the chemical level, atoms are being ripped away from each other or maybe being shoved together. We're breaking bonds or we're making bonds. Or we're doing both. We might rip something apart and combine it in a new way. Does that make sense? This is all the things that can happen. So, when we do that, we want to remember that in any chemical reaction, mass is conserved. And that's a fancy way of saying what? Yeah, very good. So we can't make atoms, so no atoms are created or destroyed. Wow, that's the worst writing anyone's ever done. In other words, all the atoms you start with, you end with. To put it a little bit mathematically, we could say that the mass of the... Does anyone remember what we call all the things you start off with in a reaction? Very good. The mass of the reactants will always be equal to the mass of the... Does anyone remember what we call all the things you end up with? Very good. Products. And when we solve equations, to me, it's often good to actually start off just by talking through them. So it's often helpful to work out reactants and products just by description first. Let's do an example. I'll give you a minute to get that written. But So for example, and we probably remember the basics of this from grade 10, even grade 9. This is the kind of classic example of a reaction of a certain type. But if I start this sentence, you can probably end it just using words, right? If we start with sodium metal and we react it with chlorine gas to form something, what's it going to form? Yeah. Yeah, and what's that mean? It means that the sodium metal, which are atoms of sodium, are going to bump into these molecules of chlorine gas. And when you're done, you're going to have sodium stuck to chlorine. Does that make sense? So, to form sodium chloride, I usually like to talk my way through, you'll be shocked to hear, I like to talk my way through a reaction like this before I do any of the math, before I work any of the formulas out. Does that make sense? I find that to be a helpful process, because then I know what it is I'm doing before I actually have to work out formulae, before I have to balance, before I have to do anything like that. Now, the law above, the law of conservation of mass, says that when this happens, there's got to be a certain recipe. There's got to be a ratio. That's not in this word equation. We could add it if we knew maybe 8 sodium metal atoms react with 2 chlorine gas molecules to form 3 sodium chlorides. I don't think that's the right answer. But we could do that if we knew the numbers, but our word equation doesn't have to have that information. It's kind of up to us how detailed it can be, and that can be helpful. I like working my way through this. Alexander, my friend, if you go see Ruby, she has got a test for you. The next step, once we just know what the reaction is, once we've kind of worked out by word equation, would be to actually write it out in formula and balance it, right? So, let's do so. We said in this example that sodium metal is going to react with chlorine gas to form sodium chloride. And with that in mind, you just want to know what everything is. What is sodium metal? What's its formula? Sorry? Na. And since we know it's a metal, what state of matter will it be? Will sodium metal be a solid, a liquid, or a gas in all likelihood when we're working with it? Solid. I suppose we could be working in a foundry somewhere and we could have it as a liquid, but in all likelihood, we're going to be dealing with sodium as a solid. So I want to start getting in the habit of including that information as well. What is sodium metal reacting with? Chlorine gas. What's the formula for chlorine gas? What is it? Cl2. Why Cl2? Why isn't this Na2? Because it's what? What's diatomic mean? Yeah, it's always found in pairs. What are the diatomic elements? Everybody up. Lève-toi. Levez-vous, s'il vous plaît. Merci beaucoup. They're just saying we need more chanting. It's time. It's my time to engage. No, team, we've got this. It's time for me to engage my inner kindergarten teacher. These are the diatomic elements, right? They're always found in pairs. Now, all together now as a team. Team, what are the diatomic elements?
Hydrogen, oxygen.
Guys, that was half-hearted at best. That was terrible. Let me just ask you. Were you proud of that?
No.
No? Were you proud of that? No, I wasn't proud of that either. Now, come on. Con gusto. I miei amici. Merci beaucoup. All right, let's go. The diatomic elements are?
Hydrogen, oxygen, fluorine.
This is somehow worse. Okay, listen. Do I have to put my mean kindergarten teacher face on?
Yes.
Is that what I have to do? Come on, all together now. The diatomic elements are?
Hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, fluorine.
C minus, sit down. Don't try and wow me at the end. You had your chance during. All right, so listen. So these are the diatomic elements, which means these are the elements that you have to watch out for, because if you're going to react with them, you can get an individual sodium atom from a piece of metal. Obviously, the metal itself contains lots of atoms, but you can pull them out one at a time. That works. But you can't pull out a single chlorine atom at a time, because that's not how they're found. They are found in chlorine gas, which is a pair. They're coupled up. So when you work with them, you got to remember to work with them as a pair. And from now on, if anyone forgets that, we'll stand up and chant together. And hopefully better than that, because that sucked. So, chlorine gas is Cl2. And then what's the last thing we need the formula for? Well, we said sodium metal is going to react with chlorine gas, and it's going to form... Oh, by the way, chlorine 2 is a gas, so we should indicate that. And it's going to form sodium chloride. Now, you probably already know the formula for sodium chloride, but sodium, how many electrons is it going to lose? 1. Chlorine, how many electrons is it going to gain? 1. Which makes for a very boring thing. The fact of the matter is that's a perfect pair, so what's the formula for sodium chloride? NaCl. And what state of matter will that be? Why solid? Why not a liquid? And not gas? It's an ionic compound. What do we know about ionic compounds? Big old dumb rocks. So in normal situations, are you going to make a big dumb rock that happens to be a liquid? Probably not. It's probably going to be solid, right? Does that make sense? Most likely. You'd have to be really hot to melt it. So it helps to kind of have everything laid out, and then just write the equation out. And don't forget that we use a plus sign to show more than one thing, right? That's more than one reactant or product. Just make sure it's a plus sign you're using. Don't write and. Don't write the little and symbol. I was marking something the other day, and there were like just 11 arrows in the reaction. Like they did like symbol, then arrow, then symbol, then arrow. But the plus sign just means more than one. So if you have 3 products, you'll put a plus sign between them. In other words, it just kind of means and. What does the arrow itself mean? This is the reaction happening. This is the reaction. It separates the reactants from the products. I never used to include that in the notes, and then I found that was something that people screwed up. So I thought, well, let's not screw that up. So with that in mind, what's our reaction? We said sodium is going to react with what? Chlorine gas. What do I put between those? A plus sign. And that's going to react. And on the other side of the reaction, what do we get? What do they form? NaCl. And that is a solid. Okay. Yeah. Then, of course, we have to look at it and ask ourselves the question, does this, as we've written it, obey the law of conservation of mass? No, why doesn't this obey the law of conservation of mass? Yeah. We lost a chlorine atom. And a chlorine atom weighs something. It weighs 35.45 atomic mass units. So as of right now, our products weigh 35.45 atomic mass units less than our reactants. And the problem with that is that we're told by the law of conservation of matter that the mass of the reactants has to be the same as the mass of the products. You can't lose atoms and you can't create them. So we got to balance it. With this, you can probably just eyeball what you need to do, but let's say you couldn't. Let's take a look at this reaction. On the left side right now, how many sodium atoms are there? There's 1 sodium atom. On the right side, how many sodium atoms are there? 1. Is that balanced? Okay, so far so good. On the left side, how many chlorine atoms? There's 1 chlorine molecule, but that chlorine molecule is made of how many chlorine atoms? 2. So we have 2. Over here, how many chlorine atoms do we have? Just 1. Okay, is that balanced? No, boo. How do we balance it? And the answer is I want 2 sodiums. Can I do that? Why can't I do that? Sorry? Okay, why can't I do that? I want 2. First thing I put it in the wrong place. So can I do that? Is that allowed? Isn't chlorine diatomic? Don't we always write as Cl2? Yeah. I can't do that because I can't change the compound. Sodium chloride's a big dumb rock. I can't put it together any way but one. The only way it can be put together is this way, which means if I want 2 chlorines, the only way I can do that is by taking 2 of the whole thing. So where does that number go? In front. When you are balancing equations, the only place you can ever add a number is in front. Do not change the formulas. You're not allowed to change the formulas. You can't change what they are. Now, what does that change? Well, now I have how many sodiums? Great, so I'm done. That's, oh no, what happened? It's not balanced anymore. I also have how many chlorines now? 2. Is that balanced now? This happens a lot. You fix one thing, yay, but we broke something else. Does that make sense? What do I need to fix now? Sorry? Yeah. Was that a hand? Oh, I'm sorry. I thought I saw your hand. I was like, yeah, give it to, and then you're like, okay, now I understand. Yes. I gotta be honest, I didn't hear a word you said, but I'm gonna assume you said the right thing, and said, put a 2 in front of this sodium. Again, can I do that? No, I can't do that. That would imply that the sodiums are chemically bonded to each other on this side. They're not. The number in front, the numbers down here tell you how the molecules are actually put together. The numbers in front just tell you how many of them you have. Does that make sense? And all we can change when we're balancing is how many we have. All we can ever change is the numbers in front. When I put that 2 there, what does that do? Well, it changes that to that. And now, finally, again, we are balanced. Yay. Huzzah. And so the final reaction would be 2 sodiums react with chlorine gas to give you 2 sodium chlorides. And that works because we have 2 sodium atoms, 2 sodium atoms, 2 chlorine atoms, 2 chlorine atoms. Everyone's happy. Again, why do we have 2 chlorine atoms here? Because this 2 applies to the whole thing. In math, we would say it's distributive, but this isn't math, so who cares? But how's that feel? Not too bad? Just bad enough? Okay? Okay. With that in mind, I want to look at just 2 types of reactions today, the easy ones. The simplest type of reaction is the type we just did. In this reaction here, we took an element, sodium, another element, chlorine, and we did what with them? Sorry? You shoved them together, stuck them together. What do we call that kind of reaction? Does anyone remember? I hate this word. Boy, I find it really hard to say. The old speech impediment comes rolling back. Synthesis. It's a synthesis reaction. I find it very difficult to say. When I was a child, I had a lisp, and I also had my R's became L's. So R's stressed me out. I'd spend a lot of time thinking about the sentence that is coming ahead of me and planning words that I can replace other words with to avoid a certain type of R, like R's next to other consonants in the middle of a word that I still can't really get my tongue around. So if I see one coming, I'm like, okay, I got to find a different word to use. And then and sometimes give me trouble. So a word where you have to go like synthesis, it's too much. I don't like it. It stresses me out. Anyway, enough about me. In a synthesis reaction, we're just putting things together. Example is what we just did. We could make a different one. As easy an example as you'll find is if you take magnesium metal and react it with sulfur, which is a solid, it'll form something called magnesium sulfide. That's just an example. This is something we can actually do in the lab. We've done this before. We'll take magnesium, we put it in a crucible with some sulfur, and then we get it going like crazy over a Bunsen burner, and you can get to form this new compound. In fact, this is a lab that sometimes we do. I haven't decided if it's one of the ones we're going to do this unit or not yet. But in general, then, what are we doing? We're taking some compound, We're taking some other compound and we are putting them together, right? Now, the thing to keep in mind, and I'm going to draw these really faintly, you don't have to bother, is these could be diatomic and they'll need to be balanced, right? So we don't know how they balance out, but all the same, we're taking two elements, putting them together to make some combination of them. Does that make sense? Does that feel okay? Yeah. Sorry? Sulfur is solid at room temperature. You can get it to be a gas. Was that your question? Is that what you said? Oh, what's the S stand for in this case? Solid. Good. What are the states of matter, by the way? Not a bad thing to remember. Recall, if I want to show that something is solid, I'll put it in an S. If I want it to be a liquid, I'll show it with an L. And I almost always use that kind of cursive L, just so it doesn't look like a 1. If we do that, it's a gas. What's the other one? And we see this a lot. Yeah, but we don't see that a lot. We're not going to be dealing with a lot of high energy plasma in this class. Sorry, guys. That field trip to the sun, she canceled. Yeah, sorry. No, we dissolve stuff in water a lot in this course. A lot, right? Probably all the labs you've done. I mean, the first lab we did was seeing what dissolved and what didn't. So the other one you might see from time to time is AQ. Have you seen that before? Did you see that in grade 10? Who said it?
Sarah. She said like 10 times.
Well, speak up for God's sakes. What do I have, Superman hearing?
You should. Actually, you do, because you can hear Sunita.
I do. Yeah.
I can't hear her.
Sunita's very quiet. Usually I'm better. Today, I don't know if I got to I don't know. Thought I used my Q-tips this week and clean the old ears out, but maybe. Yeah, I don't know. I'm having trouble hearing today, yeah. Right. Anyway, aqueous means dissolved in water. So you'll see that from time to time. And being dissolved in water gets its own name just because we do that so frequently. Water is kind of the most common thing we dissolve things in because it's by far the most plentiful liquid on Earth. Thank you, Sarah. And thank you, Angela, for letting me know. There are a few examples I want you to be aware of. The first half of reacting a metal with oxygen is completely obvious. If you react a metal with oxygen, what are you going to get? Let's look at an example. Let's pick a metal. Let's keep it easy. I'm going to say potassium. And write this small because we're going to use this space below. When potassium reacts with oxygen, what are we going to get as the product? Sorry? Yeah, potassium oxide. And what will the formula for that be? K wants to give away how many electrons? 1, which means that a single potassium would be able to give away 1 electron, 2 potassiums would give away 2 electrons, 3 potassiums would give away 3 electrons, so on and so forth, right? Oxygen wants to take how many electrons? 2, which means one of them could take 2 of them could take 4, 3 of them could take 6, so on and so forth. Where does the matchup happen? 2 and 2, which means we need how many potassiums? 2 of them. And how many oxygens? 1 of them. So what's the formula of potassium oxide? Very good. K2O. And since we're dealing with an ionic compound, this will be a solid. Oxygen is a gas. Is this balanced? No. What would I have to do to balance it? Oh, gosh, I didn't mean to do that. There we are. Yeah, if you look here, we could balance the potassiums like that. What's the problem with that? Then I'm going to have to balance the oxygens. And to do that, I've got 2 of them here. So what needs to go in front here? 2, which fixes my oxygen problem, but now gives me a new problem. How many potassiums do I have now? 4. So I need to change this number to 4. If balancing is a skill that you need some practice with, don't worry. I'm going to give you lots of time to practice that, but make sure we do practice it. Is that balanced now? Cool. You feel okay with that? Okay. That's entirely predictable. All right? Does that make sense? That's entirely predictable. It kind of doesn't even bear mentioning except this. If this is a metal and that's oxygen, obviously it's going to produce a metal oxide, right? In this case, potassium oxide. The reason that is worth mentioning is that metal oxides are how we produce bases. And this, you wouldn't be able to kind of just figure out. You have to know this. We dissolve metal oxides in water to form bases. Does anyone remember what a base is? Acids release H plus ions. What do bases release? Sorry? OH minus ions. Good. So bases are the form XOH, where X could be anything. Does that make sense? So, any metal oxide dissolves in water to form a metal hydroxide. Does that make sense? So let's write that here. K2OH, K2O is going to react with water, which is a, it's a liquid. You bet it is. And it's going to form not potassium oxide, it's going to turn potassium oxide into potassium hydroxide, which we can work the formula out of. K releases how many electrons again, by the way? 1, which means, thank you, that one of them would release 1 electron, 2 of them would release 2 electrons, 3 of them would release 3 electrons. Does anyone have the periodic table of the ions? What's the charge on the OH ion, the hydroxide ion? It is indeed -1, which means 1 of them could accept 1 electron, 2 of them could accept 2, 3 of them could accept 3. What will the formula then of potassium hydroxide be? KOH. And can we balance this? Yeah. Yeah.
In the top it says 2K2O. Why in like the bottom one it's just K2?
You could have started with 2 of them, and it would just double this whole reaction. I'm just saying, what if we just took 1 of those? But if you wanted to start with 2 of them, if you wanted this to be a direct continuation of that, that'd be fine, and it will balance. It'll just balance at twice as much. Did that answer your question? It was a good question. How do we balance this? Let's quickly look. How many Ks do we have on the left side? All right, 2 Ks. How many do we have on the right side? 1. So how do I fix that? I can put a 2 in front. Okay, does that fix my K problem? Great, okay. So now, let's do oxygen. How many oxygens on the left side? 2 oxygens. Do we see that? I've got 1 here and 1 there. How many oxygens do I have on this side? 2 oxygens. Is that good? Great. And let's check hydrogen. Hopefully we're balanced. How many hydrogens on the left side? And how many here? So are we balanced? Good. How's that feel, balancing that way? If you guys want me to, I can sort of be there. But this note, you're going to need to know that this is a kind of synthesis reaction too. And this is new to this year. Does that make sense? In the past, we've only ever done synthesis reactions of elements, right? Where it was sodium reacts with sulfur to give you sodium sulfide, or calcium reacts with fluorine to give you calcium fluoride. But to show here Sometimes we can take a compound, potassium oxide, and another compound, bless you, water, and when we're done, we still only have a compound, right? I mean, we've got two of them, but potassium hydroxide. This is also a synthesis reaction. These are much trickier to predict. Okay, much trickier. Much prickier? That's not what I meant to say. Much trickier to predict. They're much predickier. I didn't care for that. Let's just move on. Anyway, yes. It would be, potassium hydroxide in and of itself would be a solid, but if we mixed this with liquid water, likely we mixed it with a bunch of liquid water, so likely it would actually be dissolved in the water, so we would say it's aqueous. Though you could say solid. Definitely won't be a liquid because it's an ionic compound. And what are ionic compounds? Big dumb rocks. So if it formed as all on its own, it would be a solid. But if we did this by dissolving this in a bunch of water, not just adding exactly the right amount, then it's going to be aqueous. Did that answer your question? It's a good question. I should have put that there. So that's a special case. Metal oxides dissolve in water to form bases. And the nice thing is, you see how easily that actually balanced? Because this had one oxygen to begin with, and this had an oxygen with two hydrogens. When you put them together, you get the right balance of hydrogens and oxygens. These balance pretty easily. So that's a key special case. We have another key special case. And that is nonmetal and oxygen. Now, the thing you have to know is what kind of compound is this going to be if we have a nonmetal and oxygen? This is going to be covalent. And so here's something you need to know. There'll be many possible solutions, right? So I will not, in this course, make you do a lot of predicting with this. Does that make sense? Because there's not just one possible answer, there's an infinite number of possible answers. Now, having said that, there's usually a most common one, and that's usually the simplest one. So when in doubt, if I give you something and I say react a nonmetal with oxygen, probably the best answer will be the simplest answer you can find. Does that make sense? And here's a real example. If we take carbon in its solid form, maybe some graphite, maybe some coal, maybe a diamond, and we react it with oxygen, because that's what we're talking about here, we're going to get a nonmetal oxide. In this case, we could get lots of possible things. What's the easiest thing you get when you react carbon and oxygen? Yeah, because carbon wants to make how many bonds? 4. Oxygen wants to make 2. And so the easiest thing is to say, well, okay, we can make these 2 bonds here, and we can make these 2 bonds there. And what do we get? Carbon dioxide. Does that make sense? Now that's just, again, there's a million solutions. Could we have gone carbon, carbon, double bond there, double bond oxygen, double bond oxygen? Could we have made that? Does it work? Yeah. Could we have made a million different things? A billion different things. You can make an infinite number of things. So if I give you a question where I give you a nonmetal and oxygen, you're going to have to find a solution. And as long as your solution is valid, I'm going to give you the marks for it. But my advice would be find an easy solution. Don't spend an hour like making the craziest thing you can think of. Keep it simple. In this case, it's hard to get simpler than that. How do we balance that? It's balanced. Isn't that fun? Nice when things are balanced. But just remember, this is only one of many possible solutions. So why mention this at all? Well, first to show that covalent compounds undergo synthesis reactions too. We are mostly going to talk about ionic compounds in this course. Why? Yep, exactly right, which makes it much easier. So that's the reason. We deal with ionic compounds in this course first because it teaches you the principles of chemistry in an easier way. When you get to covalent reactions, that's a class of chemical reactions we call organic chemistry. Organic chemistry just refers to the reactions between carbon-based things, so not ionic reactions, but covalent reactions. Organic chemistry is famously the course that makes people question their will to live in university. Organic chemistry is, have I ever told you my first year or second year organic chemistry story? I had this doctor, her name was Christina Pauls. Used to go to her lectures. Main thing I remember about Dr. Pauls is she was Scandinavian, and she would sometimes put an S on the singular form of word, and then pluralize a word that was supposed to be singular. So she messed that up, and she had a really kind of funny accent. And that's really all I remember from that course, because I didn't understand anything. And I had 98 going into the final exam of the first half because I was good in the lab. All my lab marks were good. And Sarah Chirico, my friend, was very good at all the assignments. And we used to go to her house, and our assignments were different, but she would help me with them, and I would make dinner. So that was our arrangement. So I had a really good mark, but I didn't know a thing. I didn't know anything. So 2 weeks out from the exam, I went to Dr. Paul's office. I was like, I'm really drowning. And she's like, oh, Joe, your marks are good. I'm sure you'll do good on the exams. And I was like, okay. And then I wrote the exam, and I remember it was 10 pages. There were 10 questions. And page 1, I was like, okay, I'll come back to that. And page 2, I was like, maybe I'll come back to this one. Page 3, I was like, ooh, that's pretty tough. Don't know what that is. I'll come back to that. And by the time I got to page 10, I was an hour into this exam, and I realized I hadn't even written a single thing down yet. And when all was said and done, I did so badly that in a class of 500 people, the professor called my home. And this is back in the day of landlines, my parents answered, and they're like, Joe, there's someone on the phone for you. And it was Dr. Pauls, and she was like, Joe, you did very bad on exams. And I got a 17%. And she made a deal with me. She said, if you promise not to take my third year course, I'll pass you. And I said, okay. And then I actually went back and retook that second year organic and did well. But it was hard. Organic chemistry, covalent stuff like this, gets tricky. It gets confusing. I'm not going to throw much of it at you. Does that make sense? We start with ionic for the most part, but I do want to mention something. Metal oxides dissolve in water to form bases. On the other hand, non-metal oxides dissolve in water to form acids. Metal oxides form bases when you dissolve in water. Non-metal oxides react with water to make acids. You, come get your note. It's right there. So, I picked carbon dioxide as an example because this is actually something we do a lot. Where is a context in which we dissolve carbon dioxide in water? You might have one at home. Anyone have a soda stream? Anyone seen a soda stream?
No.
Anyone ever had a soda pop?
Yes.
Yeah, right? How do you make soda? What do?
You make some things.
You make the bubbles? Is that it? Every time you're drinking a pop, there's little elves in there blowing into straws.
Yes.
And you're like, oh, that sure is delicious. No, have the bubbles get in the pop. Who put the bubbles in the pop? How'd they do it?
Chemical.
I guess, yeah. What do they do? Yeah, what they do is you have a big canister of CO2 and you pump carbon dioxide through the water. And that gives you soda water. All right, so you look here. Carbon dioxide, which is a gas, can react with water. And some of it just dissolves. And then when you take the pressure, if you put it under pressure, it'll stay dissolved. And when you release the pressure by opening the cap, it starts to bubble out. And that's cool. But some of it doesn't just dissolve. Because if you ever let pop go flat, or you ever let soda water go flat and then sipped it, does it taste like regular water anymore? No. It's sharp and kind of got that acidic flavor to it, right? Because it's formed an acid. Yeah.
Am I the problem, or does that say a C? I don't know if I got it wrong.
Well, okay, let me ask you.
What?
Admittedly, is that the best uppercase letter D that anybody's ever drawn? No, I'll grant you that.
Oh.
Now, having said that, context clue. Do you think that in this conversation of acids and bases, I've told you that non-metal oxides react with water to form ACIOs, a word you've never heard before? Or do you think that it has formed acids? Which one? Just out of curiosity, which one of those two things do you think has happened?
There's always no word to bring it up.
You're like,
Every single time.
oh, this is a Latin word for this.
Exactly.
And then we're like,
You're always bringing up
okay.
different words. I don't know.
Okay, I mean, in fairness, I also said out loud like 11 times acid. But hey, no, hey, you
You know how many times
you do
I
you.
copied
All right,
down those
okay,
things?
all right. Shut up. Okay, all right. I'm glad we had this talk.
No, he's like, imagine like a 6-year-old watching your videos, right? And he's not listening to what you're saying.
He'd be doing much better than this.
Okay. I write down what you say, and then it's like you write something entirely different so many times. Like, I'm done trusting.
Can I say that's fair? That's fair. I'm chastised. I apologize. I will try to be better. Again, context clues. We're training a generation of scientists here. Context clues. We make observations about the world around us and then make reasonable inferences. Okay, but having said that, if your reasonable inference is that I sometimes throw random Latin words at you and Greek words, that's fair. I accept that and I apologize. Okay, now, what acid is this going to form? Well, it could form a bunch of different ones, but what if we literally just shove these two things together just exactly as is? No balancing or anything. What would you end up with? How many hydrogens? 2. How many carbons?
2.
As written. 1. Careful. How many oxygens as written?
3.
Yeah. And as it happens, is that a compound? H is hydrogen. It takes a +1 charge. What's CO3? That's an ion. What ion is it? Carbonate. What charge does it take? -2. You don't have to have that memorized, by the way. Which, as it turns out, where does that balance up? Now you could also have this turn into the carbonite ion, things like that. But it just happens that because covalent things can come together in a bunch of different ways, just shove it all together and you get a real thing. As it turns out, 2 hydrogens balances perfectly with the CO3 ion. This actually works out every time. Every time you do one of these, you can just smush them together and get something that works. Does that make sense? And so, what do we call this acid? The acid of the carbonate ion. We drop the 8 and replace it with ic acid. Good. So this would be carbon dioxide reacting with water to form carbonic acid. Now again, the important thing isn't that you know this reaction. I just want to show that you can also get synthesis reactions starting with a covalent compound plus a covalent compound. And interestingly, this is a covalent compound reacting with another covalent compound to form an ionic compound. Totally different thing. That can happen. Does that make sense? And the important thing in this case isn't to know this specific reaction, but I do want you, generally speaking, to know that metal oxides react with water to form bases, and non-metal oxides react with water to form acids. Right? Cool. And then, on the other side, we get decomposition reactions. But of course, decomposition reactions are just synthesis reactions run backwards. If you understand synthesis reactions, you understand decomposition reactions. It's just the reverse. In decomposition reactions, we just say that, some compound, AB, and who knows how many of them we need, is going to break down to give us some amount of A by itself and some amount of B by itself, right? That was supposed to be the general form. That's okay. This was supposed to go here, but that's okay. We'll put the example here. Example, what if I had, I don't know, well, what do I do here? Oh, that's a good one. What if I took Cu3N2? That's copper 2 nitrate, or not nitrate, copper 2 nitride. If we break that apart, what are we going to get? What two things? Forget the balancing of it. Copper nitride will break down into copper and nitrogen. And what do I need to remember about one of those? Very good. Which one? Is the copper diatomic? The nitrogen's diatomic. Good. There we go. That's a decomposition reaction, right? Just take the thing and just break it into its two pieces. Now, is it balanced? No, but this one balances pretty nicely. On the left side and on the right side. On the left side, how many coppers do we have? 3. On the right side, we have 1. On the left side, how many nitrogens? On the right side, how many nitrogens? So there's only one thing we need to fix. What do we need to fix? Copper, and I just need to do that, right?
No.
I put it at the front. Why can't I put it here? What would that mean? That would mean that this makes a compound of copper stuck to two other coppers, right? Like a little copper triangle. But that's not what we're saying. What we're saying is it just releases copper atoms, but that we get how many of them? 3. By the way, copper nitride, is that going to be solid, liquid, or gas in all likelihood? What kind of compound is it? What do we know about ionic compounds? So, state of matter? Solid. Maybe we do this by heating it up. The copper we get will probably be solid. The nitrogen, on the other hand, will probably be a gas, if we're working at anything around normal temperatures, right? Decomposition reactions are very straightforward. Now, we do have a couple of cases, all right? And I could give you special cases all day long. I thought instead, let's just look at the special cases that kind of reverse the ones from the other side. Does that make sense? So radicals, and we'll stick to a carbonate as our example. Let's say, for example, we have magnesium carbonate, MgCO3. I picked magnesium because magnesium takes a 2+ charge, and carbonate takes a -2 charge. So the nice thing about those is they just balance each other out. Does that make sense? So we'll go magnesium carbonate. Carbonates decompose. Well, look at the previous page. It's the same idea. What can this release? And if you don't remember, that's okay. You don't need to predict this. We're going to write it down. But carbonates decompose by releasing CO2. And again, what I just want to show you is that once you have radicals, sometimes you start getting covalent reactions happening. We're not going to do a ton of covalent reactions. In fact, we're going to do like 4 of them, and they're all going to be today, and that's kind of the last we're going to deal with covalent reactions. Because again, what do we know about covalent reactions? They're messy, they're complicated. But I want to see a few. Does that make sense? Because they get interesting. So if this released CO2, what remains in this compound? Is the carbon left? Now we just got rid of it. How many oxygens did we get rid of? 2 of them. So how many is left? Does that work? We should check it. Mg takes what charge? Oxygen takes what charge? Which means that the formula remaining is MgO. Does that make sense? So by releasing CO2 and a metal oxide, this is not the only example. It's the only one you need to know. Again, I could make you memorize 1,000 reactions. This isn't a second-year organic chemistry class. We don't need to do that. But just so you know, like sulfates do the same thing, but they don't release carbon dioxide, they release sulfur dioxide and a metal oxide. Does that make sense? But it's the same basic principle. They're a bit more annoying because you have to balance them, but they work nicely. I picked the carbonate example because every single time the carbonate example self-balances, because oxygen takes a -2 charge and so does carbon dioxide. So the nice thing about these carbonate decompositions is you never have to balance them. You release the carbon dioxide and you form the metal oxide, and they always just balance themselves. It's beautiful. They're the easiest reactions. Once you do 2 or 3 of them, you'll see that they're always the exact same thing. One more example, which is again just the exact opposite of what was on the previous page, decomposition of hydroxides. What hydroxide did we do on the last page? Potassium hydroxide? Okay, we'll do a different one here. Let's do sodium hydroxide. It's the most common hydroxide. What's the formula of sodium hydroxide? Na takes what charge? +1. Hydroxide, OH takes a -1 charge, so the formula would be NaOH. When this decomposes, again, it's the opposite of how we formed hydroxide. On the previous page, what did we have to react something with to get a hydroxide? We had to react a metal oxide with water. So if you go the other way, if you decompose it, you're going to get a metal oxide and water. So hydroxides decompose into metal oxides and water. Well, we all know the formula for water. What's that? That was easy. And then sodium oxide, we're going to have to work out. What charge does sodium take? +1. So one of them would release 1 electron, 2 of them would release 2, 3 of them would release 3. What about oxygen? What charge does it take? -2. And where does the nice match happen? Like that, right? So how many sodiums do I need in sodium oxide? How many oxygens do I need in sodium oxide? So the formula is Na2O. And there we go. Is this balanced? No, but it's really close. What's it need? We put 2 there. And now how many sodiums do we have? And here? Cool. How many oxygens do we have? And here? Cool. And how many hydrogens do we have? Very good. And over here? So are we balanced? Cool. All right. These are all special cases. And that's good. There's some homework here. Your homework, you have a choice. You can do this, or my preference, actually, because you get immediate feedback. Yes, ma'am. Oh, I didn't. I should do for both. What would magnesium carbonate be? Solid. It's a big dumb rock. Carbon dioxide will be a gas. Magnesium oxide, big dumb rock. So it's going to be a sodium hydroxide, big dumb rock. Sodium oxide. And we're doing this by heating it. So this would actually probably release gaseous water. You know what I mean? If you put liquid, I wouldn't mark you wrong. But the way you decompose something is under heat. It's going to be real hot. And when water is real hot, what state of matter is it? It's gas. Okay, listen up. There's a homework sheet attached here. You can do it if you want. The thing about the homework sheet attached here is you won't necessarily get immediate feedback. In fact, not necessarily. You won't get immediate feedback. If you go to Teams and the little practice app I've made, which is clumsy, I will grant you, but if you go to that little chemistry practice V2 app, here's what I like. Go to reactions, see here, and then say you want to do synthesis and decomposition, and then you can start out with nothing tricky. No radicals, no multivalent metals, just simple, right? And here we go. Write the decomposition. Let's do an easy one. Write a balanced chemical equation for a decomposition reaction that yields potassium. So it yields. What's that mean? It's a decomposition, but the products are going to be potassium. What's the symbol for potassium? And chlorine. What's the symbol for chlorine? Cl2. It's diatomic, right? What would we have had to start with to get potassium and chlorine? Potassium chloride. How many electrons does potassium want to lose? 1. How many electrons does chlorine need to gain? So what's the formula of this thing? KCl. Now, are we balanced? How many potassiums on the left? On the right? So far, so good. How many chlorines on the left? How many on the right? What do I need to do here? Okay, now how many potassiums on the left? How many on the right? What do I need to do? Do you see that? And then we can check it. And it'll give me the equation. And you can do that all day. So listen, for your homework, do this till you get 10 right. And I don't care how many tries it takes you. If it takes you 50 tries to get 10 right, awesome, you're learning. If it takes you 10 tries to get 10 right, awesome. Thrush taught you real good, or whoever you had, Alaschuk, or did anyone else teach grade 10 science? I don't think so. Did I? I didn't. Miata, right, yeah. One of the 3 taught you real good. But it doesn't matter if it takes you 80 tries to get 10 right. That's okay, you're learning the whole time. Does that make sense? I cannot stress enough, this app is clumsy, it's stupid, whatever, but there's no better way to learn because you get feedback immediately. Does that make sense? By the way, every once in a rare while, like 10% of the time, it'll tell you that like the balancing is like 990 to 990 to 990. I don't know why it does that, but just ignore those ones, okay? If you see a number in the hundreds, Calford wouldn't have this coding problem, but like 1 to 100 times it shoots that at you, just skip it and move on. That's not the real answer. Your lab notebooks I want, line them up at the back. Yes, ma'am? How do you what?